Hello chemistry friends. I'm going to work through some problems in chapter 11. So this is example 11.1 on page 365 of your book. A chemist wishes to make calcium carbonate by using this reaction. Na2 CO3 plus CaOH2, turns into CaCO3 plus 2NaOH. See if you can see all that. If the chemist mixes 50 milliliters of 1.23 molar Na2CO3, so I'm going to use 50.0 milliliters of this, and it's 1.23 molar with an excess of calcium hydroxide. That means I have plenty of this, so I don't have to worry about it. How many grams of calcium carbonate will be produced? This is just a stoichiometric problem. Remember, when you have a balanced chemical equation, if you know one thing, you can calculate everything else. So I know I have 1 mole of this plus 1 mole of this is going to make 1 mole of this plus 2 moles of this. So first I need to remember that molarity is moles per liter. So that tells me how many moles I have. So you're going to have to figure out how many moles you have by doing 50 milliliters. I'm going to use a different color, see if pink works better. I have 50 milliliters of it. I'm going to change that into liters because this is moles per liter. And I want to figure out how many moles I have. So that's the same as 1 liter over 1,000 milliliters. So that really means I move my decimal place 3 places this way. So I will have 0.050, actually, liters. Now I can convert that into moles. So I will take my 1.23 moles per liter. 1.23, this is moles per liter. And that will give me 0.0615 moles of Na2CO3. So if I want to figure out how many grams of this I have, I just need to know my ratio between this and this. Well, they're both 1. Remember, if there's not a number there, the stoichiometric coefficient is 1. So that means if I have 0.0615 moles of Na2CO3, I can multiply that by, I have 1 mole of that here, Na2CO3, for every 1 mole of CaCO3. That will convert that to how many moles of CaCO3, and it should be exactly the same. So it'll be that times 1 divided by 1 is going to be the same as 1 mole of CaCO3. I'm rewriting it just because you won't be able to see. But I'm not done because the problem asks me for how many grams I need. So then I'm going to have to go to the periodic table. I'm going to have to remember how to calculate how many grams are in 1 mole of CaCO3. So I take 1 times my calcium, which is going to be 40.1, 1 times carbon, which is 12.0, and 3 times oxygen, which is 16. And it can figure out that there's 100.1 grams in every mole of calcium carbonate. So I take my 0.0615 moles, my moles are going to cancel, and I will end up with 6.16 grams of calcium carbonate. Okay, so it's just a stoichiometric problem. You just need to remember that molarity is moles per liter. Okay, so I'm going to move on. So this is molarity, capital M, and it's moles per liter. So just to make things, you know, super fun, they also have something that's called molality, and they put it in the same chapter just to, you know, be super confusing. So if molarity is moles per liter and it's a capital M, a small m, not to be confused with meter, which is also small m, small m is going to be your molality, and that's going to be how many moles of solute. Remember, we talked about a solute and a solvent last week. Your solute is going to be the solid that you dissolve into. Your solvent is going to be the liquid that it gets dissolved into. So this is going to be the solute, that's your solid, and divided by your kilograms of solvent. So that's going to be your liquid. So let's say you dissolve salt into water. That's going to be your solute and your solvent. So it's going to be how many moles per kilograms of solvent. So it's a little confusing because they're so close, big M, small m, but this is going to be your moles per liter. This is going to be your moles per kilograms, so it's a weight of your solution, solvent. So let's do example 11.2. Chemist mixes 3.4 moles of NaCl, which would be your solute, in 4.5 kilograms of water. What is the molality? Super easy. You divide your moles over the kilograms, and that's going to give you your small m, your molality. So it's going to be 3.5 divided by 4.5. It's going to be 0.76 mole, small m. Next one, this is example 11.2, second part. If a solution is made by adding 45 grams of zinc chloride to 150 grams of water, what's the molality? Well, remember, that's moles of solute per kilograms of solvent, so you're going to have to convert your 150 grams to kilograms. So in 1 kilogram, I have 1,000 grams. So I can just remember to move my decimal place over 3 places when I'm dividing by 1,000. So I'm going to have 45, oh, did I do that wrong? I did. It's 45 grams of my zinc chloride. I wrote the wrong number. Helpful if you write the right number. Zinc chloride divided by, oh no, I didn't. Oh, all right, I did it right. 150. It says I'm on solvent. I'm getting confused because they're doing it in the different order than I am. So I have to first figure out how many moles of solute I have. So if I have 45.0 grams, I'm going to have to convert that to moles. So up in the periodic table, I'm going to take 1 times zinc plus 2 times chloride, which is going to give me 136.4 grams and 1 mole of zinc chloride. So that's going to be equal to 0.33 moles of zinc chloride. And I have 4 significant digits here, but I only have 3 here, so I should have 3 here. So I have another 0 there. All right, so then I just take my moles of solute, which is 0.330 moles, and divide it by kilograms of solvent. So it's 0.1500 kilograms. 3 significant digits here, 4 here. So my answer is going to have 3 significant digits. 2.20 molar. So that's going to tell me my moles of solution. My molality of the solution. All right. So now the biggest part of the thing this chapter covers is going to be your boiling point elevation and freezing point depression. We kind of touched on this last week, where we talked about when things are dissolved into solution, how many pieces they break into. And the more pieces they break into is going to be, it can affect how how much lower it makes the freezing point, like when you add salt to ice, or how much you can raise your boiling point, like when you add salt to your boiling water when you're making noodles. So the nice thing is that the equations for both of these are almost exactly the same. So your freezing point depression this is a delta. It means change in. So the change in your temperature is going to be a negative I. This is freezing point depression. I don't know if you can see that. Can you? Yeah. Okay. So it's going to be a negative because it's going to lower my freezing point. So it's negative I, and remember I is the number of ions or pieces that your solute breaks into, times K sub F, which is, it's a constant, and it's for your freezing point. It's your freezing point depression constant, times your small m, which we just realized was our molality. So that's your moles of solvent per kilograms of solute. I said that wrong. Moles of solute over kilograms of solvent. So it's your solid over your liquid. Okay? So we're going to have to know, remember, I'll write small m is moles over kilograms. Okay. So it says when 15 grams of sodium chloride are added to 100 grams of water, what's the change in the water's freezing point? And they have to give you the freezing point constant. So they're going to tell you that your K sub F is going to be 1.86 degrees C per molar. So we need to figure out, put it into this form, and that's going to tell you the amount that it changes, okay? Be very careful when you're reading the question. If it's asking you what your new freezing point is, or your new boiling point is, or if it's asking you what the change is, because that's two different questions. So it says, what is the change in the water's freezing point? So we're going to solve for delta T. So again, we're going to have to know what the I is for sodium chloride. Remember, sodium chloride is an ionic solute. So it's going to break into a positive part and a negative part. So its I is going to be 2. Breaks into 2 pieces. So your delta T is going to be negative 2 times your K sub F, which is 1.86 degrees C per M. And we have to figure out what my M is. And my M is going to be my moles per kilogram. Well, I can change that to kilogram real easy by dividing by 1,000. So it's going to be 0.100 kilograms of water. But this I have to change to moles. So 15.0 grams of NaCl. I need my grams to cancel out, and I get 1 mole on top. So from my periodic table, I take 1 times sodium, 1 times chlorine, add it together, and it's 58.5 grams of NaCl in 1 mole. So that gives me 0.256 moles. So I take that moles of NaCl over my 0.1000 kilograms of water, and that's going to give me my small m. So that's going to be 2, oh, did I write that wrong? I did. Oh no, I didn't. Okay, that's going to give me 2.56 small m. So then I take those numbers. So this is going to go times this times 2.56 m. So the m is going to cancel out, and all I'm going to have left is my delta, my degree C. So my change in temperature is going to be 2 times 1.86 times 2.56. And I don't have my calculator here, so that's going to give me negative 9.52 degrees C. Now, if it asked me what the new freezing point would be, I'd have to know that this is water, and water freezes at 0 degrees C. And so this lowers my temperature negative 9.52 degrees C. So my new freezing point would be negative 9.52 degrees C. It would be the same if it's water. But let's say on the test they gave you something that wasn't water. Let's say on the test they gave you something that was a different solvent, and the freezing point is 10 degrees C. Well, then you're going to have to make sure that you subtract that from the freezing point that they give you. You know, they couldn't make it easier. They're going to try to trick you. So if they ask you what the change is, make sure you give them the delta T. If they ask you what the new temperature is, you would take the old freezing point and then subtract whatever your delta T is, and that'll give you your new freezing point. Okay, because, you know, they couldn't make it easy. All right. All right. If they are asking you what the boiling point elevation is, that means how much your solute is going to raise the boiling point. So freezing point depression is change in T equals minus I times the K sub B, K sub F times your M. This is going to be basically the same thing, only now we're talking about how much you're going to raise your temperature. So it's going to be delta T equals positive I, because we're raising the temperature a certain amount, times your K sub B, which again they have to give you, it's your boiling point elevation constant, times your M. So it's exactly the same thing. They're just going to give you a different constant, and now you have a positive I instead of a negative I. Calculate the I exactly the same way. So let's see. In cooking, a pasta chef adds 20 grams of table salt. 20 grams, and there's just two, actually there's just one significant digit of NaCl, table salt is NaCl, to 1.45 kilograms of water. Oh look, they already gave it to you in kilograms, that was nice of them. It brings the water to the boil. What's the temperature of the boiling solution? Okay, so now this doesn't say what's the change in temperature. It says what's the new temperature. So just make sure when you give me you're going to calculate the delta T, don't stop there, okay? That's going to be 1 point. Knowing the new temperature is going to be another point on your test. So first, again, we have to figure out the I. We know the I of sodium chloride is going to be 2 because it breaks into 2 pieces. Your K sub B they have to give you. So that's going to be 0.512 degrees C per M. So we need to calculate our M. Our M is going to be the moles of sodium chloride over the kilograms of solvent. They already gave us the kilograms of solvent, but they didn't give us the moles of sodium chloride, so we have to take 20 grams times 1 mole over grams of sodium chloride. And what was that? 58 something. 58.5 grams, which we calculate by 1 sodium and 1 chloride from our periodic table. And my grams cancel out, and I'm left with 0.3 moles. And again, I only have one significant digit here, so my answer is only going to have one significant digit. So then I'm going to take, to figure out my M, I have to take 0.3 moles over NaCl over my 1.45 kilograms of water. So my M is going to be 0.2. And again, I just have one significant digit. So now I plop it back into this. I'm going to write it here just so I have more room. Delta T is going to be a positive I now, which is 2, times my K sub B, 0.512 degrees C per M, times my moles, which is 0.2. So that cancels out. And so my delta T is going to be, what is it? 0.2 degrees C. Okay, so that's not my answer though. My question said, what is the temperature of the boiling solution? Well, I hope I know that water boils at 100 degrees C. So if I add this to it, it's going to be plus 0.2 degrees C. And so I'm going to, it's actually 100.0 degrees C. So then my new temperature, my new boiling point, is going to be 100.2 degrees C. So make sure you take that extra step. Read your question really carefully. When you think you have your answer, go back and make sure you answered the right question. Okay, so again, if you are calculating your sodium chloride, probably is going to be on your test. It breaks into 2 pieces. Your I is going to be 2. But make sure you know how to figure out your I. We did a couple problems in class last week. So let's just refresh. If you have something that's CaNO3 and there's 2 of them, if something is ionic, it breaks into as many pieces as you have, but if you have parentheses, remember that's a polyatomic ion. It does not break apart. That part sticks together with covalent qualities. So you're going to break into your 1 for your calcium and 2 for this part. It breaks up like this. NO3, NO3. So my I for this is going to be, I is going to be 3. Okay? If you have something like a sugar, that's a covalent. It's a covalent compound. Covalent compounds stay together in one big chunk. They don't break into ions. So if you have something like C6H12O6, like a sugar, it is not going to break into 6 plus 12 plus 6 pieces. It's just not. It's going to stay together in one piece. That's why you don't add sugar out to your salt on the sidewalk. I have added sugar to my boiling corn though, but anyways, the I of any covalent compound is going to be 1. If you get a I of more than 5, it's wrong, okay? Remember, so if you have something that's ionic, it's going to break into as many pieces, but just keep in mind, if you have a polyatomic ion, anything in a parentheses, those don't break apart. So again, if you have MgOH2, how many pieces does it break into? This is the positive part, and there's 2 negative parts, so that breaks into 3. So I is going to be 3 again. Really hard, the hardest one is going to be something that's calcium carbonate. This is doesn't have parentheses around it because it's only got 1. But carbonate is a polyatomic ion, so it doesn't break apart. So you have 1 from your calcium and 1 from your carbonate. So your I is going to be 2. That's your hardest one. Okay. Easy one, MgF2 is going to have 1 from your Mg and 2 from your F2s. So your I is going to be 3. It's going to break into 3 ions. Those are pretty much all you have to, all you do. Remember, if you have anything that starts with carbon, C12, C2, C1, anything that starts with carbon is a covalent compound. The I is going to be 1. Okay, so just, I'm sorry I'm not feeling good, so I'm not coming to class tomorrow. So just don't want to get anybody sick. So just make sure you know the difference between small m, molality, which is your kilograms, nope, it's your moles per kilogram of solvent. And your big M from the last chapter is going to be a little bit different. It's going to be your moles per liter. So if they give you a weight of your solvent, you know you're using small m, just so you know. If they give you your liters, you're probably going to be talking about molarity. Okay, hopefully that is clear. You should be able to do your lab at home if you have a thermometer and some salt. If you don't, I'll try to do that lab later, but right now I'm going to go lay down. So, okay, see you next week.